Welcome to standard reduction potentials. So, the flow of electrons from an anode to a cathode is spontaneous. If it's not spontaneous, then the reaction doesn't go. But if it is spontaneous, then what is our driving force? Why are the electrons moving? Because there's always got to be some driving force for any process. If I drop a ball, that ball falls because the potential energy of that ball is dropping as it's gravitationally attracted to the Earth. So that driving force is that gravitational pull on the ball. So if the electrons are moving somewhere spontaneously, then there must be some force pushing them from one place to the other. So we want to know, why are our electrons moving spontaneously? So electrons are flowing from the anode to the cathode because the cathode has a lower electrical potential energy than the anode does. So we can talk about potential difference. This is the difference in electrical potential, and it's measured in volts. So we have some electrical potential of our anode and some electrical potential of our cathode, and there's a potential difference between the two, and so the electrons are moving from one to the other. 1 volt is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. So remember that joule and coulomb and volt are the SI units. Joule is the SI unit of energy, and coulomb is the SI unit of charge. So volt is the SI unit of electrical potential. So 1 volt is 1 joule per coulomb. And the electromotive force, sometimes called EMF, is the force required to push electrons through the external circuit. So this now brings us to cell potential. So we symbolize cell potential with a capital E and then a subscript cell. This is the potential of the entire complete cell, and this is the electromotive force of our cell. So this is the cell voltage. This is how much of a push there is, how much force there is behind the electrons. The larger this force is, basically the harder the electrons are being pushed through our external circuit, which means the more work we can do with those electrons. For a spontaneous reaction, then, the E cell, the cell potential there is greater than 0. For a non-spontaneous reaction, the E cell or the cell potential would be less than 0. It would be negative, which would then mean that the electrons would tend to flow the other direction. So for 1 molar solutions or 1 atmospheric pressure for gases at 25 degrees C, these are standard conditions, remember. The standard EMF or the standard cell potential is called E cell naught. And for this reaction then, we've got our zinc going to zinc 2+. If we set the concentration at 1 molar here, and the copper 2+ going to copper 0, the copper 2+ ion concentration is set at 1 molar, then everything is in its standard state, because standard state for solids is the pure solid there and here, and standard states for aqueous ions are concentrations of 1 molar. If this is true, then our standard cell potential happens to be positive 1.10 volts. The standard cell potential is not always going to be plus 1.10 volts, although it will be for this reaction. But what the standard cell potential is depends on what the reactants and products you have. So if we change out copper here for something else, then the cell voltage will change, the standard cell potential will change. So we can conveniently tabulate electrochemical data using standard reduction potentials. So these are the standard potentials that are measured relative to some standard. We're using standard state here. So the EMF of a cell can be calculated from the standard reduction potentials. Note that we're using reduction potentials because reduction is simply the opposite of oxidation. So we could use both reduction and oxidation potentials, but then our table has to be twice as big. If we just use the reduction potentials and then we just flip the sign on those potentials that we want to be oxidation, then our table doesn't have to be as large. Our tables are already generally a few pages long anyways, so doubling the length of them just really isn't necessary. So then the complete cell potential at standard conditions, so E cell naught, is equal to the reduction standard potential, so this is at the cathode, plus the oxidation standard potential, this is at the anode there. And in the book there is a table, this happens to be table 20.1 for standard reduction potentials in water at 25 degrees C, and in the back of the book there is a much larger appendix containing standard reduction potentials. And so you can see various values ranging from negative 3.05 through 0 to positive 2.87, and we've defined this reaction to be 0. This is the reaction of hydrogen ion plus 2 electrons goes to hydrogen gas. And we're defining that as 0 because we need a 0 point somewhere. It doesn't really matter what we pick. We just picked that one because hydrogen is the first element. And so that's a nice, easy one to pick. And then everything else is relative to that. So there are some that have potentials that are standard reduction potentials that are negative, some that have standard reduction potentials that are positive. And so, of course, the more positive it is, the more likely that reaction is to occur, or rather, the more driving force there is for that reaction to occur. So if we pair up something like hydrogen with something like fluorine, we expect that because fluorine is more electronegative, it will be able to steal electrons away from the hydrogen. And that is in fact what we see. If we have hydrogen here and fluorine has a reduction potential of plus 2.87, and hydrogen has a reduction potential of 0, because we've defined it that way. If we look down here at the bottom, we've got negative 3.05 for lithium. We expect lithium to be less electronegative. Well, we know that it's less electronegative than hydrogen is, so we expect hydrogen to be able to steal electrons from lithium, but hydrogen cannot steal electrons from fluorine. And so, based on the standard reduction potentials that we have there, we now have a way of relating how strong of a reducing agent or an oxidizing agent some compound is. Higher on the table, the higher the value is, the stronger that species is, or the more likely that species is to become reduced, which means it's a stronger oxidizing agent. The lower on the list it is, the less likely it is that that species is reduced, the more likely it is to be oxidized, which means the stronger of a reducing agent it is. All right, so our oxidation process then is the reverse of our reduction process. So if our oxidation looks like this, then our reduction looks like that. So we've just flipped the reaction around. And because the oxidation process is the reverse of our reduction process, then the standard reduction potential is simply the opposite sign of the standard oxidation potential. And this means that our standard cell potential is equal to the standard reduction potential of our cathode minus the standard reduction potential of our anode. So note that I've changed the sign here from a positive to a negative and changed the oxidation potential to a reduction potential. So now everything involved here on the right side is a reduction potential. One of them is for the cathode and one of them is for the anode. And then we use the standard hydrogen electrode, which we abbreviate SHE, as our standard. I already talked a little bit about this, that we needed a 0 point. We've just happened to pick the standard hydrogen electrode where we have hydrogen ions going to hydrogen gas. We're defining that reduction potential, that standard reduction potential, to have a value of 0. and then we're measuring everything else relative to that. So in this cell, we've got a platinum electrode. That then would be written in over here, platinum solid. That's our electrode. That's in a tube, placed in a 1 molar hydrogen ion solution. So if we have a concentration here of 1 molar, that means that we have a very, very low pH, and this is a really acidic solution. And we have hydrogen gas that's bubbled through our tube, and basically the hydrogen gas is then in contact with our platinum surface, and we also have the aqueous hydrogen ions there in contact with our platinum surface. They can react. So let's look at this half reaction. We have our zinc solid goes to zinc 2+ ion. We have our concentration of 1 molar, which means that this is at standard state. And we can then measure our standard cell potential relative to our standard hydrogen electrode. That's our cathode in this case. And when we plug in our values, we measure positive 0.76 volts, and we know that the standard reduction potential of this standard hydrogen electrode is 0 volts, and that means that we can figure out what the standard reduction potential of our anode, this one, is, and that must be negative 0.76 volts. So now we go through and we do this for a large number of reactions, and that's how we create our table. So you don't have to do this, we've done this, and again, there is an appendix in the back of your book, at least if you're using the Zumdahl textbook, that has a large number of these, and generally any textbook that you have will have an appendix like this. So standard reduction potentials have to be written as reduction reactions, not as oxidation reactions, right? They're reduction potentials, not oxidation potentials. So we have the zinc 2 plus 2 electrons goes to zinc 0, and here our voltage for that reduction is negative 0.76 volts. And so since our standard potential there is negative 0.6 volts, we can then say that the reduction of zinc in the presence of the standard hydrogen electrode is not spontaneous. In fact, the reverse reaction will be spontaneous. So the oxidation of zinc with the standard hydrogen electrode will be spontaneous. And again, this makes sense because hydrogen ought to be able to take electrons away from zinc, because zinc is a metal, it's got a lower electronegativity than hydrogen does, so hydrogen ought to be able to steal the electrons. So the standard reduction potential is an intensive property. That means it's not an extensive property. It doesn't change when you change the stoichiometric coefficients. So if we double the number of zinc ions, so if we reduce 2 zinc ions using 4 electrons to 2 zinc atoms, the standard reduction potential is still exactly the same. It doesn't change. If it were an extensive property, then the reduction potential would change. Now, the current that we're getting out, the electron flow that we're getting out, the charge flow that we're getting, that value does change. So that is extensive. But the voltage is an intensive property. It won't change. So reactions with a cell potential, a standard potential that are greater than 0 are spontaneous reductions relative to the standard hydrogen electrode, and reactions with a standard reduction potential that are less than 0, they're negative, are spontaneous oxidations relative to the standard hydrogen electrode. And the larger the difference between our standard reduction potential values, then the larger our cell voltages. So the more positive the value of our standard reduction potential, the greater the driving force is for reduction. The lower that value is, the greater the driving force is for oxidation instead. So let's look at, or let's consider a table of standard reduction potentials like the one in the back of your book. We can use this table to determine our relative strengths of reducing and oxidizing agents. And the more positive the value of our standard reduction potential, then the stronger the oxidizing agent is. And this is written in the table as a reactant. And the more negative the standard reduction potential, the stronger the reducing agent. And we can then use this for predictive. One reactant can spontaneously oxidize another one. So again, fluorine can oxidize hydrogen or lithium. Nickel 2 plus can oxidize aluminum solid, and so on. So we can look at some reactions here, right? We've got lithium plus an electron goes to lithium solid. The standard reduction potential there is negative 3.05 volts. We've got our fluorine over here. The standard reduction potential is plus 2.87 volts when we have fluorine gas gaining 2 electrons to become 2 fluoride ions. When we then add those two reactions together, we've got our standard complete cell potential of the standard reduction potential for our cathode minus the standard reduction potential for our anode. So we've got this value, the plus 2.87 volts, minus a negative 3.05 volts from up here. And that gives us 5.92 volts. And because these are the two extreme values, any other value that you get will be less than that. It will be somewhere between 0 and 5.92 volts. So that was standard reduction potentials.